This is a short overview presentation on lifelong machine learning. Some context for why we need lifelong machine learning. The current ML approach has led to superhuman accuracy on many specialized tasks such as image classification. This is primarily due to the availability of abundant labeled data. But there are many tasks that does not fit this description. Either the data is limited or the task is too unstructured to collect all possible data points. A model is limited only by its training data and is going to fail on new observation if there is a mismatch from the training examples. This is where lifelong learning comes into picture. Lifelong learning systems and algorithms provide a way to acquire new knowledge incrementally, retain and consolidate past knowledge, and inductively transfer learned knowledge on new tasks. A precise definition of lifelong learning is, however, difficult to provide, mainly because it's an active area of research and any definition will be highly dependent on the task being solved. As a motivation, there are real world use cases that requires such a learning system. Lifelong learning systems can take a form of software or can be deployed in hardware with a lot of sensory inputs. Though we don't have precise definition uh, of lifelong machine learning, we can always describe what do we want from such a system. In that regard, lifelong learning systems can be based on some basic principles. In other words, pillars of lifelong machine learning. The first is continual learning. It is the ability of learner to incrementally add new knowledge without interfering with any knowledge acquired in the past. The second is internal exploration. It is the ability of learner to organize itself by interacting with the world. This means even in the absence of data, a learner should be able to learn from its own action. Third is context modulated computation. This is the ability to know when something to be learned and when not to learn based on the context. Finally, new behaviors implies that the learner should be able to apply past knowledge on new unseen scenarios. For the rest of the presentation, this is an agenda. First, I'll provide a formal definition of continual learning, then problem statement, followed by how such algorithms can be evaluated, and then three different approach category that is current in research. This will be followed by some discussion on internal exploration and self-supervised learning approach to enable such ability. Finally, some discussion and relevant research in context modulated computation. In the To formally describe continual learning, we must differentiate between learning phase, also termed as knowledge acquisition phase, and prediction phase. During knowledge acquisition, as time progresses, the learner receives labeled data dx and dy that follows some data distribution. Note the subscript t in p of t of x. This means that data may not be IID across time. When learner is required to predict, the observation x can be from any past distribution till the current point of time. Now, having formalized the continual learning, there are some extra things that needs to be considered. The most important ones are the order in which the data is being observed. Second, task boundary, type, and finally the memory and computational constraints. If task boundary is continuous, additional assumptions can be made, such as task observed at time point t is similar to task observed at time point t minus 1. A simple approach to incrementally train on new data is to keep storing the data and retrain on all data till convergence. This is not a practical approach if memory and computation is bounded. Another approach is to start with the parameters from the previous task, train on the current data, This is also a problem since such training can interfere with previously learned parameters, degrading the model performance on previous tasks. This is actually termed as catastrophic forgetting or catastrophic interference. If we develop approaches that solves for catastrophic interference, proper evaluation metrics is required. Apart from accuracy, two other metrics that are widely used are forward transfer and backward transfer. Forward transfer measures models' ability to carry related information from past tasks and use it to improve the current task. Backward transfer is opposite. It measures the model's performance on past tasks given that model is trained on the task observed at time point t. The first approach, which is dynamic architecture based, is to increase the model's capacity when a new task is encountered. The addition of new parameter often needs explicit procedure, that is, how many parameters to add. Also, this method works when task boundary is well defined. In the picture, when task 2 is introduced, new parameters are also added, and the shared parameters are retrained. That is, training update only affected the subset of parameter. Similar things can be observed from task 2 to task 3. Regularization-based approach focuses on regularizing the loss on new tasks to minimize the forgetting of previous tasks. This does not require addition of any additional parameter in the model. The main idea here is to first estimate the importance of each model parameter of the previous task and then penalize the changes to each parameter mm, proportional to this measure. In other words, more important a parameter is for solving the previous task, less changes will be done to it during the optimization process. Third approach is based on storing a representative dataset from the past task and use it along with current task to train the network. The representative data need not be stored explicitly. Instead, can be sampled using techniques like generative adversarial networks. This approach was covered in detail in the previous presentation. The next topic is internal exploration. As discussed, it is the ability of an agent to interact with the world and acquire knowledge without external supervision. The closest technique we have in machine learning is self-supervised learning. The main idea behind self-supervised learning is to invent a new task, also called pretext task, for which supervised labels can be created on the fly. Then train the pretext task, then train the model on pretext task, and finally extract the learned representation to solve other related tasks, also called downstream tasks. This process can be described as starting with a set of hypotheses, learn the best representation for such set of hypotheses, and then search for the best hypothesis using the learned representation. There are some well-known pretest tasks that contains a large set of hypotheses. In computer vision applications, one such task is to jumble up the patches in an image based on some permutation and then ask the network which permutation was that. By solving this task, the learned representation encodes semantic ordering in naturally occurring images. Another well-known pretext task is colorization. A colored image is converted to black and white image, where colored image becomes a reference level. The network is asked to predict the color at pixel level. The representation encodes the objectness, depth, boundary, and related properties. In a similar way, a good representation of motion or time series action can be learned from video. If frames in the video is suffered and network is asked to ask for the correct ordering. Other than computer vision, the self-supervision has been widely used in NLP tasks as well. With a large corpus of textual unlabeled data, a lot of pretext tasks can be invented. One simple example is to predict the next word given previous word list. The learned embedding can be used in other tasks such as translation and sentiment analysis. The third part of lifelong learning is context modulated computation. The main idea with this is that in real life dynamic environment systems, an agent must modulate its action, and this is inspired by neuromodulatory mechanism in human brain. In the paper Uncertainty Based Modulation, which we have referenced, author describes a lifelong learning system that builds on the concept of uncertainty, also called vigilance parameter, which controls how similar a sample bottom-up input needs to be to an existing top-down expectation in order to incorporate the sample. If similarity metric does not pass the vigilant criteria, then system is considered uncertain and it engages in a different learning mechanism in order to introduce the sample into the knowledge base. This way, the system progressively adjusts its knowledge base based on the encountered uncertainty. You can look into the paper for detailed discussion. So, this was a high level overview of lifelong machine learning.